All right, welcome to my, I think, almost 10th or 11th webinar, ultrasonic resonance frequency tracking using an Arduino. Um, I hope these are keywords like frequency tracking Arduino. I think that brings a lot of interest in something very practical that you can get your hands on. So sometimes drive circuits similar to ultrasonic transducers themselves sometimes feel like they're out of reach and something you need to purchase or something you can't understand. But I'm going to be showing in this presentation, we're going to be driving a mesh nebulizer using kind of a circuit built with basic components and even going an extra step and doing frequency tracking. So there's just a little bit more going on than just driving the device. So yeah, let's go to the next slide. So I'm very excited about this presentation. The reason is I've had the components to do it for more than 2 years. So I ordered this board here, which is what we're going to use for frequency generation. I ordered it 2 years ago, two years ago in like 2 months, and I ordered the little amplifiers that I'm going to be using, which are like just pretty small, but they can do 18 watts at least at audio frequencies. That's the claim. I ordered that almost like almost 2.5 years ago. So it's kind of exciting to kind of bring it all together, even though it's kind of it's a small project, but it is nice to use the stuff you bought from a while ago. I don't know if you engineers have that feeling. You bought something that was interesting and you got to it finally. So that's excited. Here's the outline of the presentation. First, choosing a transducer. It's not obvious when I want to present to you something that works and you can see it work, and it's not a very it's an easy to understand application. It's also very common. A lot of my clients use atomizer circuits for many different applications. So it's atomizers and nebulizers are of very much interest to people, engineers in general, projects, and also this specific advantages to demonstrating the circuit on this device. And I'll get into that. I'm going to be speaking about drive circuit requirements. So what do you need in a drive circuit in general? I'll tell you that pretty fast. And I'll show you how do we generate frequency and what are the aspects around that. And also amplifying the signal and conditioning the drive signal so you can actually properly drive your transducer. And also this extra step, feedback control, which brings you one step up from just kind of setting, doing the hand thing where you're like sitting there with your function generator and trying to look at waveforms on an oscilloscope to get resonance and things like that. So we're not going to do that. We're going to let the microcontroller, the Arduino in this case, handle it. And the Arduino that I'm using, I don't think I listed anywhere, but I guess it's going to be obvious from the pictures. It's our Arduino Uno microcontroller, but it works on whatever Arduino you want to use or microcontroller process. You should be able to port the logic and the style of and the implementation there too. Then we're going to actually do the thing. I'm going to show you what I did to create it. It's a little bit, wires everywhere type of operation, but I think there's some legibility in there still. And I'm going to discuss the Arduino code, the device characterization, like what actually happened. Did it work or not? Was there mist coming out of the thing or not? And I talk here about improvement areas. So I don't have a poll set up in Zoom, but I'm going to ask you all at the end of this presentation if you would like to see a different topic or you'd like to see perhaps this circuit improved for the next webinar topic. It's nice to build. It's nice to, I see a lot of areas, obviously, it's where this circuit can be improved. It was mainly kind of a quick development. But if you want to see that, we can do it, and we can kind of step through different improvement areas and increase your understanding. I believe having a good connection with how transducers are driven will give you a further depth of understanding about their operation. It's not just transducers are not just like items on a web page that you order and you stick this one with this one and it just works. There's much more complexity to that. I think the 16 participants who are joining live, many of them, I guess I'm one of them, can attest to the difficulties that would come if you just assume that things work. They don't, and you need to understand why they don't. And understanding each component, including the circuit, which is super important, is going to be a big factor. So why did I choose a mesh atomizer? And this kind of got screwy here. That's my finger. All right. Okay. So this is the mesh atomizer that I purchased, and I'm going to be sending out the notes here. So this is a link to a picture of a mesh atomizer. They're pretty small. They're like about this big, like the size of a penny or so. And here's a link to the one I bought off Amazon. I didn't use the driver itself, so it has a driver in the body, but I actually just took the top off, so I have the container of liquid and I have the atomizer. It's easy to implement, and here's a kind of a look at the atomizer and my finger. Whichever you'd like to look at, go ahead. So there's a mesh part in the middle. If you have any questions on what this and then the atomizer resonates. It resonates like in a planar vibration, and this mesh kind of goes back and forth, and then it sucks fluid into it and it spits it out. So there's a kind of container of fluid behind this atomizer, and that's how it all works. So this is kind of a really common device. I think it's $50 for this specific device, and if you wanted to buy the components, even it comes with the drive circuits, probably like $10. I ordered that too. It didn't come in the mail. I don't know what happened to it. Maybe I got to complain to them about that. But anyways, so why do I choose a mesh atomizer? So it's common. There are many clients and people doing mesh atomizers. I'm not singling any client out, or this is not inspired for any certain client, but it's just so common that this is one of the most common applications that I get for consulting. So lots of people are doing it for inhalation, for smell, for humidification, for environmental control. There's so many applications, and folks are realizing that and trying to utilize it and running into issues. So let's start there. It's also low voltage slash low power in comparison to other transducers. So I don't have to create like a 100-watt supply or a 1,000-watt power supply. It's relatively easy to maintain. You can see it work easily. Like when it's on and working properly, it throws out the mist, right, from the atomized water. So it's easy to see it work. So that gives us some satisfaction. And I can also convince you guys that it's not just the waveforms on the screen. There's actually something happening. But there are also a lot of drawbacks to using this device for demonstration, and I'm going to get into that. You're going to see that in a few slides. But before that, I'd like to give a word from our sponsor, which is me. And it's my company, Ultrasonic Advisors. So I founded this company several years ago, and I provide a lot of different expertise to clients. I have gotten into specializing in doing finite element analysis with COMSOL and delivering that for clients in terms of troubleshooting, optimization, design, just answering kind of questions like, why does this effect happen? I've had a lot of projects in terms of ultrasonic bolt clamp transducers, Langevin transducers. I've worked with atomizers before as well. I've worked with companies who just want, an expert on their, at their meetings, for example, just to kind of review their progress and ensure that they're doing things according to the best standard. So I, there's a whole host of different things. I don't want to say jack of all trades, but I'm very deep in each area of ultrasonic engineering. And I'm sure if you feel that your project can benefit from my help or my expertise, hands-on or advisory work, contact me. You have nothing to lose. Contacting me, and this is only for companies, not for students. So apologize about that, but I hope that students can attend these webinars and get the benefit from that point. Let's talk about the ultrasonic drive circuit with feedback. And this is specifically the one that I'm going to be showing. Now, many of us are probably already familiar with different types of feedback circuits, what's measured, what's controlled. This is going to be a simple one meant to be, let's say, in a portable device or something that's not taking all lengths to control your transducer, but you do want some control over your variability. So we have a microcontroller here, and a microcontroller works with our frequency generation IC. So one thing is to note that in Arduino, it can't produce specific frequencies, like in very small step sizes. You can actually turn analog, turn the digital output off and on for square waves, for example, but you can't you can only do it as far as the clock cycle is concerned. So you can do it in terms of clock cycles, but to produce very fine frequency steps is kind of challenging for this. And I have a whole video on like doing clock cycle kind of work. Arduino has a module called tone, which also works, but as you go to higher frequencies, that gets an issue. I had a video with assembly code, and I showed that. Maybe I'll go on Microsoft Edge and I'll just show you like what that video. But anyways, so you have to use a frequency generation IC if you want specific precise frequencies, which we often do for resonance drive, right? Then we need an amplifier because this IC is not meant to drive a transducer directly, nor does it have the voltage, nor can it supply the current for driving a transducer directly. Usually if transducers are anywhere from 20 to a few hundred volts and AC, and it's usually between, let's say, 10 milliamps to a few amps. Those are kind of the ranges of transducers in general. We'll see about our product that we're describing here today, the atomizer, but we'll keep going. So we need a transformer because likely the amplifier is not made for your transducer, so it's not going to be well matched in order to deliver the maximum power. In many cases, the amplifier is overrated for your transducer, but that's okay, especially if you're plugged into the wall. You have a medical device or you have a surgical device or welding, like it doesn't matter about being matched. But when you start getting to very high power levels, you do need to match that power. You can't build an amplifier to that spec. So anyways, we bought off-the-shelf audio amplifier, a transformer which steps up the voltage and matches the output impedances more or less. We have the transducer and also then something to measure current. I'm going to be describing this current measurement, but it's kind of nice because our microcontroller cannot sample fast enough with enough resolution that actually I haven't checked if anybody knows how fast you can sample an Arduino analog output. Let me know. I actually don't know. But I assume at this frequency it's going to be tricky. So why not go with something more stable and something dedicated? So you can do you can buy like an RMS measurement, IC integrated circuit chip, or you can do more basic peak detect circuits, which I'm going to be showing. So yeah, there's somebody's mentioning here in the comments on some microcontrollers you can actually sample as fast as tens of kilohertz. Yeah, so what if you're driving a 100 kilohertz device? Well, you just keep sampling until you get the max, right? That could be that could be like an approach to overcoming limitations. But we're going to overcome limitations in a more smooth way here. But many, people have, there's so many different options with microcontrollers. It's kind of fun. It's really fun. If I were to do my career over, I think I would do microcontroller work as a profession, but alas, I'm an ultrasonic advisor, here to stay for you all. So we're going to the next slide, but please leave comments, and I think it just makes the presentation more interesting for me, and I think the people listening. Yeah, if I'm talking very fast, which I feel like I am, you can watch it slow motion on YouTube. So if you enjoy slow or if you enjoy quick, whatever you want. I'll be posting this up later. So here are the requirements for the drive circuit. Not going to give too much detail because I have other resources for it. So I will, there's a comment. I'm going to get to that right after I finish the slide. So here are the drive circuit principles. You need to drive it with an AC waveform that sources and sinks current. It's not enough to have like a battery and attach it and detach it from the transducer. You have to form a path where you charge the transducer, you could say, and discharge. So there has to be current flow both ways. So no diodes on the AC part, right? So you need current to flow both ways. The amplitude of the voltage should be high enough. I'm very much generalizing, not speaking too much engineering terms. You should have enough voltage, and the driver should be able to provide enough current. So who here knows what happens if you drive a transducer or a device that with an amplifier that can drive the voltage but can't drive the current? What happens? If you have an amplifier that can, does anybody know what happens if you have heat? That's one. So like overload, I guess that's one option. One thing. Does anybody else know what happens? Like, let's say it doesn't blow up. and it just runs stable. What basically happens is the voltage on your device will decrease. So if you're driving at, let's say, 10 volts, but and your transducer wanted, let's say, 1 amp, but you can only provide 500 milliamps, the voltage will actually decrease on the output side of the amplifier to meet that current, the maximum current. And it'll heat and it'll kind of like so it'll basically not deliver the maximum power to your load. That's what's going to happen. So you'll still it'll still work theoretically because there's an output impedance. There's a drop in voltage in the circuit. So the circuit itself, like just like we have batteries and we talk about like series resistance of a battery. There's like a effective series resistance or impedance of an amplifier. So you need to make sure that you are matching your amplifier to your transducer, and that's what a transformer is for. Unless you like designed your amplifier from scratch, which is probably not the case that you want to be doing. So drivers should be able to provide enough current. And some drive circuit principles, you got to generate the correct frequency. And however accurate you need to be. I think if you find the quality factor, which defines a bandwidth, let's say the bandwidth for the quality factor is, let's say, 100 hertz, you probably want to be driving at least like 5 hertz or something like that. In 5 hertz steps, or you practically determine that in order to like kind of get around that area. If you have a so you want to be having precise frequencies and doing that at higher frequency levels. Because your Arduino is just fine going from like a 1,000 hertz tone to like 1,001 hertz. It's fine doing that. But now when you're going from 100 kilohertz to 100 and 100 kilohertz and 1 hertz, that's in increments, it's not going to be able to do that. Or even in 10 hertz, it's going to be a very unnatural process, I guess. That's what I would say. I think there are tricks, but using kind of the more straightforward method will be best for you. And if you have, if you have just a static frequency, like you just need to drive with 2 megahertz and that's it, your Arduino can provide that. And if you look up on my YouTube channel, it's one of my most popular videos, Arduino drive frequency generation for transducers or something. There's a video like that. It's one of my most popular videos. It'll have that if you don't want to use another IC. So we're also going to do current measurement, and we're going to correct for current by changing frequency. So this is kind of a non-standard way. Normally what you would do, you would control voltage to get to a target current, and you would control frequency to get to a target phase. That's the typical method. But because we're limiting ourselves, you can actually, if you just keep the voltage constant, or let's say the drive output constant, or relatively, or open loop rather, and you change the frequency, you can actually bump into the resonance frequency just by changing frequency, and that'll obviously increase current. So you just change frequency to actually monitor current. And I'll just draw a diagram here. I probably should have described it. I'll be doing it on time. Not bad. And yeah, and I'm just warning that I hope there's nothing freezes when I try to do all this, because my computer hasn't been playing the nicest in the last few days. So you folks know that this is the impedance response, more or less, of a transducer. And I'll just draw this Z and draw this omega. I'll change the color. And if you were decreasing your frequency, if frequency goes down and you start from here, your current will increase. Is that clear? So if your frequency goes down, because if you look at current, your current is maximum at resonance, and it goes down, it goes to 0, goes very low at anti-resonance, right? This is the current. This is I. So when you decrease frequency, or you get closer to the resonant frequency in either direction, the current is going to increase. So you can actually do a feedback from frequency and current. So if you have a current set point of this, you can go up and down in frequency in order to make sure that stays stable. If anyone has any questions on that, please let me know now, or hold your peace until the end of the presentation. So okay, hope that's clear. Anything else on that slide? Yeah, so typically you would control voltage to get to a target current and frequency to keep a target phase, a relative phase distance from the resonant frequency in order to maintain stability. Um, there are disadvantages to this, which is why it's not used in general, but this is a portable circuit. We're working with limitations. We want to keep things very simple. We want I want everyone to be able to actually do it easily. So we're going to keep going. This is the frequency response. Now, this is the one thing that really shocked me about these devices. Not literally shocked me like a piezoelectric shock, but it shocked me in terms of like, wow, there are actually transducers who have impedance responses like this. The resonance region. This is the without any fluid. I did the resonance frequency response. Kind of blue is impedance, so it's like really all these like kind of funny spurious peaks from 90 to 120 kilohertz or so. That is not the response of many transducers. That's why it kind of confused me about how, but it actually works, and there's still power that's generated, and there's a whole bunch of reasons why this happens, because you have a thin membrane which is resonating, you have symmetry issues, you have glue, a lot of different things which you have holding of the edges. There's a lot of different problems with this, but it's still a functional device. So it kind of taught me about imperfection in transducers and trying to deal with that, the reality of not everything is a bolt clamped transducer being held at the nodal point. That's the reality. So that I have to deal with. Not everybody has to deal with that reality if you don't work on various transducers. So this is with the fluid filled chamber. So adding fluid usually damps a lot of resonant modes or loading. So there appears to be, what I would say, if you look at the phase here in red, there appears to be like two dominant resonant features, one around 110 kilohertz and another resonant feature around 94 kilohertz. Both of these, believe it or not, produce, actually, you probably will believe it, they both produce atomization. They're probably related or similar modes. The mesh is probably doing something funky and different at one versus the other. They're probably related. And there's no clear resonance or anti-resonance, not very clear, but it is the response of the device. So there's a comment here. Maximizing current would yield electrical resonance, but mechanical resonance could still be off. Yeah. So in this case, I won't be maximizing current. So I didn't do a current maximization program. Just kind of getting ahead. I did just a set point. So I set the microcontroller to kind of go back and forth around this area once I found the target. So in this case, like the mechanical resonance and the electrical resonance, they're like, it's such a messy response that even if you're drawing power, you're not necessarily creating atomization. So this is a very peculiar device for perhaps many of us, and how kind of strange the coupling between electrical and mechanical dynamic performance, and also actual practical performance in terms of spray rate, how all those related. But it's an easy device to set up, and you can see it work. So I think it's great for a demonstration. So thankfully, there are resources online already on how to program this. So what I basically did, so Arduino, I mentioned it can't provide good frequency resolution. We want good frequency resolution for driving transducers. So the Arduino programs just kind of communicates through I2C communication through to this board, which is purchasable. I have a link here on like a lot of details on this board and using it within Arduino. It's what I use to create this. So I'm not going to go over it in detail because it's like right here, and it's quite frankly how I learned it. So I think you can do it too. And I do provide the code that I use too, so you have that as a reference. So the board provides a 3 volts positive square wave, and the frequency can be reprogrammed really fast, about every millisecond. I kind of did an informal check using some Arduino functions, and it was about one every millisecond I could provide a new frequency, which is probably more than what you need. As I'm going to show you in a few minutes, I actually originally had a delay time in the loop to like let things settle, but I just put the delay time at 0 because it seemed to close loop just fine in this application, and it wasn't unstable. But putting like averaging and things are always a good idea. in general. So it has a couple of channels, so you can actually provide 3 signals. Not that you would need to, but if you could drive, let's say, and 2 of them are unique. So you can drive 3 signals, 2 of them are unique, but I think, yeah, you could probably actually drive 3 different atomizers using this board, because it can provide 3 unique frequencies. 2 are related to each other, but just in terms of range, not in terms of resolution or the exact frequency. So that's kind of neat, and you can provide 3 inputs from the analog to kind of do that, to kind of do the feedback work. Are there any questions on this, how to generate frequency? The code is like simple, and if any of you actually have a problem with it, because I had a few snags, then like send me an email and I can help you actually, because it should be simple, and I hope that doing all this will actually help you learn it more than hearing about it, and being curious about what the results are. So here's a teeny amplifier, 18 watt. It's about this big. It's kind of pretty small. I actually have it in the corner. I'll just show it on the video. This one kind of broke. The potentiometer broke. It's just like this small. So this is actually what you need to drive. And this is an audio amplifier, so it's not like a single frequency designed to be the most compact or the most efficient, right? When you start, because it's an audio amplifier, you just want good, clean signals across all frequency ranges. There's a trade-off in terms of power consumption. However, I do believe that the power consumption of this device, I think you can actually build a commercial device atomizer using this. I don't doubt that. It's efficient enough, and you can change these you can build a custom device around it to actually get to this 18 watt value. I'm not sure if this exact design does 18 watts, and there's this like output capacitor. And so here are the pinouts. I'm just going over this so you folks have no problem replicating my work. And there's another comment. I will get to that right after I get to this finish this slide. So here are these ground pins which are connected. This is where you put your input, this pin, and this is where you put your voltage. I used a rechargeable 9-volt battery, which kind of it charges via USB, so it doesn't provide 9 volts. Strangely enough, it's like more like 7.5 volts. So, and here's a schematic. And these I have the links here, so you can purchase it. I mean, I bought this so long ago that the old link didn't work anymore, so I had to like find the same thing from a different vendor, but it's the exact same thing. So this is the thing about to notice here is that there's a capacitor on the output here. This is specifically for speakers. So because speakers are inductive loads, so if, low frequency on an inductive load is a short circuit, so it kind of prevents that from happening. I saw a lot of different people using this module, but changing the capacitor on the output. I guess in theory you could short this capacitor. There were some issues, and I didn't bother with it right now. And you can change these parameters. Here's the potentiometer, which you can just adjust. We're going to be driving with the square wave, which is also kind of odd for an audio amplifier. It doesn't really want to be square wave driven, but we are, I'm trying to demonstrate a certain thing here, and I'm not trying to demonstrate everything. So yeah, there's two comments. One comment is it correct that it doesn't matter if you're generating a sine? Let me just actually I can copy it. I can get it, and we might go long today, so just note that, because I like to answer the questions, or at least give my opinion on it. Is it correct that it doesn't matter if you're generating sine or square wave, since the transformer is going to round out the square wave anyway? The transformer doesn't really round out the square wave, but so it will carry those extra harmonics through it. Now you're going to get a lot of influx current, which can have negative effects on how the transformer behaves. So yeah, in general, you want to put a couple of filters, let's say. But I was hesitant on putting those filters at the clock generator output, simply because I was wondering if it doesn't like to draw a lot of current. It likes to be driven to a high impedance load. So I didn't want to break it the night before I was making the making the circuit and everything. So yeah, and the nice thing about using a sine wave, it's easy to analyze the output. You don't get all these other harmonics on the output, and then it gets confusing to analyze. Somebody mentioned, I'm going to post this here. So here's a question about phase lock loop by a few degrees from the zero crossing to hit a favorable impedance rather than mechanical resonance. The goal was to maximize the transferred power of matching the impedance of the amplifier. Yeah, I think that that makes sense. That you that that the amplifier can drive with more power at a different frequency. Um, um, but yeah, it would drive more power. It might drive more current. Yeah, but yeah, I had to think about that, how exactly that would work. But in general, you can't. The transducer does have a variety of characteristics you technically can choose from. You can also choose high impedance point to drive at anti-resonance if you choose. Um, you'll need a lot more voltage. So usually we like to drive at resonance because circuits are just easier to play with. At they like more current. Many transducer designs go with more current. There's also less other considerations. But resonance is more unstable than anti-resonance in terms of drive conditions. So yeah, but this is an interesting kind of idea, and I'm sure it's true. I just don't have experience doing it, so so additional question here to this one. I'm gonna not make sure nobody's names will ever appear on these. If they do, then I'll immediately take off the video. Just by the way, nobody's videos or names or chats being recorded. But for megahertz transducers, transformer will require more you know more specialized transformer. Yeah, that's correct. Because you have to switch at faster frequencies, which is also more you have to get special components, and you also have to special transformer. So that's absolutely true. Um, and somebody actually made another good comment here. This is a frequency generator board for sinusoidal output. Uh, yeah, that seems good. Yeah, I'll probably try that out soon. That looks good. If you're using, for example, if you're driving a MOSFET, which would probably be the more logical case when you have a square wave generation, then you do need a square wave, right? To turn the MOSFET off quickly, or the transistor. But yeah, sine wave is going to be better for the envelope amplifier because you'll get a lot less garbage out, and you're going to dissipate a lot less energy by driving these random harmonics that are just like driving some capacitance off at 300 kilohertz. It's draining a lot of current maybe, but it's not doing a whole lot of anything. So I like that. Thanks for that recommendation. And how good the sine wave is? Pretty good, not too bad. That's all I'll say. uh, there's no acceptable noise level. It kind of depends on your application or what you want. There's not an unacceptable or acceptable range. It's what you want and how much power is that all those other frequencies dissipating. Um, so and this is not rated to do 100 kilohertz. They don't advertise this to be able to go to 100 kilohertz, but you can. So audio amplifiers to drive ultrasonics are very common, especially at the 40 kilohertz range. Surgical transducers that I know of are based off of audio amplifier circuits. You can build an amplifier based off discrete components, but why do that when you do have products existing that you can just jump into? So I don't know the acceptable noise levels, but just a square wave is going to be terrible if you're talking about noise. But yeah, so here I kind of just looked at this plot, and I was looking at kind of eventually you have about 500 ohms here. I think the lowest point is 302 as it shows, but it might increase when you add larger power levels. So I did kind of some basic math just to get an idea. This is not something you need to be following, but just for our theoretical discussion of power and matching impedances. So the amplifier probably does 18 watts into 4 ohms, which is a inductive load, a speaker, and it's going to require 2 amps. If you do 2 amps and into a 4 ohm load, it's 16 watts. So you're going to kind of need 2 amps with 8 volts RMS. So it's definitely not large enough to drive your transducer. And I got to also let you know that the battery that I have, the 7-volt battery, is not going to be able to drive an 8-volt signal from the amplifier. Amplifier means amplifying the signal input. It doesn't mean amplifying the voltage supply input. All right. So you can only if you buy an amplifier, you're only going to get as much voltage as it produces internally to supply it. So, but sometimes there's step up voltage, like you can provide 5 volts and there's a step up DC step up to 20 volts or whatever. But in this case, your supply voltage limits the maximum voltage you can do. So I had 7 volts, so the output would be like 2.5 volts approximately, because there's some drop, right? So the output voltage was swinging between like 2.5 volts to minus 2.5 volts, which is kind of small. So hey, I need a lot of amplification here, because these transducers at least are driven with 40 volts, 50 volts, 40 volts peak to peak. And I know when it works because then it sprays, right? So I did not bother measuring the response of the provided circuit that came with it, but and yeah, the custom winding, one more person mentioned custom winding for higher frequencies as well as lower ones. Like in this case, I did kind of custom wind it just so I can modify it. So I didn't. There's like a circuit in here, so I didn't use that one. I didn't measure it. I just was kind of trying to get to the end. So and we're marching along. All right. So basically, like I just said, okay, maybe the amplifier is going to want to drive 10 ohms, which is probably not true because there's like an output capacitor and other components. But if we're kind of going from 5 ohms, 10 ohms to 500 ohms on the transducer, impedance ratios 50, and perhaps we need 7 windings or ratio of 7 in the transducer. More practically, I found out that like, yeah, with the transformer that I was using, which is about a size of a ring, like a ring that you wear on your finger, you want to this is like a very like rough, very rough like thing that I did. I wound the transformer, the blue winding, and I wanted to make sure that when I connected it, the voltage dropped on the output. That means there's a good amount of current being drawn from the transformer. So it's like it's matching somewhat well. That's kind of what I did. It's not much more complicated than that. How I started, and then I just wound the I just kept winding the output, and I wound it till it worked well. And that's kind of as simple as it gets right now. There wasn't perfect matching, but hey, I do know that there's definitely power delivered. The primary winding is good. I could have wound this a bunch more times and still not really still not really take or impact the amplifier a lot. And there's kind of calculations you can do, and no matter how many calculations you do, if you build it, it doesn't work, it doesn't matter. So so sometimes you can build it, and if it works, it doesn't matter. You don't have to do any calculations. What do you know about that? I have clients like that. I'm like that too, in some ways. But when you're trying to make it perfect or very good, then you do need to do calculations along with experimental work. So I do show the inductance values too. So this was like, I think I also bought this from Amazon. It just tends to be easier for me to do that with the 2-day shipping. I don't have to pay for it. So yeah, this is about the size of a ring, and I'll give the inductance values too later. So the second side is about 30 wounding, and you can also like wind the secondary side with smaller gauge wire. It has less current, and not like it really matters for this frequency and these current levels, but you can do it. You can do that. You can make the windings tighter and do things like that too. So here's the transducer. Here's the fluid container. The fluid gets filled there. The transducer is here and inside on the other and here's kind of how I attached it. I wanted to show you these are the pins that actually go to the body, which would drive the transducer, but I actually attached these spring clips that I have. It was kind of a fun to see that these little holes that are already on these spring clips. And let me know if you want a link to them, because they're going to match perfectly with this. Or you could solder. I don't want to solder directly onto it, and it's kind of like really an awkward thing to have an alligator clip. So these spring clips work well. And I just you can solder to a lot of different items. You have to just sand it first, and then you can solder to it. It's easy enough. There's a and it's a little bit messy, I'll say, but I'll explain each kind of part. So this is hooked up, and this is kind of just a little stand that I have just to make sure things are sitting properly. So this is how I made the connections to the transducer, and positive, negative, it doesn't matter here. Here's a picture of the setup, the microcontroller, the rechargeable 9-volt battery, which only provides 7 volts. Here's a switch connecting the battery and not connecting the battery. This frequency generator chip right here, if I can zoom in, if it's going to let me zoom in. All right. It is powered by the Arduino. You can only do between 3.3 and 5 volts for it. So it's powered by the Arduino, and there's let me just there's connections, and you can find that on that website that I posted earlier, and I'll be posting these notes too. This is just a thin plywood board that I just attached things to, obviously, because I wanted to keep things fireproof, right? Or not. But nothing should catch fire because I attached this extruded aluminum tube to to the MOSFET, right? Because I took it off, it's easier to mount it. I super glued this on, and what else do we have? And you're gonna see here this current measurement peak detect circuit in a second. But here's the output of the transformer, and it kind of goes to the clips. And I didn't make wires long enough, and there's kind of things flying all around, but all the grounds are the same. I'll let you know that for now. All the grounds connect together. Even on the output side of the transformer, I didn't make it isolated. I actually grounded that side too. So because I needed a reference point for measurement, and I'll explain about that in a second. So if you start having questions, because now is like the part where I think that people would have the most questions of like, hey, I don't understand how that fit together. This board right here is just to make sure all the grounds are connected, have a place to put them. This whole entire circuit could probably fit on this board here. But yeah, I did not I like things open when I'm explaining, also looking. So yeah, I can, could you also set your current measurement reference on the battery side rather than the transformer side? That is a great question. And that is actually very true. That would work, measuring how much current is drawn from the battery, basically how much current it takes to drive this. That would work, except that like the dead current or the current that it takes in normal operation or off resonance is very similar to the current that it takes on resonance. So it doesn't like change in power very much. So you're going to get a very small current change. So yes, when you do drive with more power, it will draw more power and current, but it wasn't enough really to affect to be able to be measured. And I'll give some more excuses right now. I also didn't want to make another op amp, like amplifier circuit, to amplify that voltage, because I have to have it. I'm having it grounded, and if I don't have the battery grounded at a true ground, like the rest of the things, then it's going to be kind of confusing. So I chose not to do it, and I chose to use the output. But there are potentially many points that are affected by the maximum power or more or different amounts of current. And yeah, like I mentioned, this amplifier seemed to be taking the similar power levels and voltage levels at resonance and not at resonance, so it didn't help. So I actually wanted to do the measurement at the transducer. You could also do it at the output here. This is how medical devices do it a lot. Like they are not allowed to do measurements on the transducer itself because that's connected to the patient, and we don't want the patient to be kind of grounded, right? And we don't want to make a ground loop and shock the patient with a surgical device. So they do all the measurements on the primary side, and the secondary side is isolated completely. There are just there are like mathematical kind of equations, and based on experience and testing, you can know how much voltage and current from the primary side and what the phase is going to be on the secondary side on the transducer. Some of that can be calculated, but in practical purposes, you can just do that measurement, and it's going to be there's going to be a higher level of abstraction too when you take those measurements, you put in the microcontroller, and you got to do some control around it. So that's the case there. So you can do it also on the and there's a specific reason I used the secondary side and not the primary side. So I'm going to explain that in a second too. And I have to, oh boy, I froze. So hold on. I usually freeze over here. Okay, so I'm going to be taking this slowly because I might freeze while this is playing. All right, I'm gonna put my head to the side and play this video. So this is the circuit. I'm just kind of showing you around. You can also buy like this thin plywood. And so, okay, let me just explain what I did. And hopefully it doesn't stop. But when I switch this button, it connects the power to the amplifier. That's why you'll see the light turn on. When I press this button, it resets the microcontroller to run for 3 seconds, like find the target current set point, and then continue. So I'm going to be I have a couple more videos and pictures and circuit diagrams too to show. But when I press this button, it restarts the microcontroller, which then starts the search for resonance. Maybe it'll be one of my novels one day, The Search for Resonance, where things just don't make sense. Hussein's book is going to show you how to search for resonance. What do you think? Can I get a thumbs up in the chat for that one? But okay. I don't know if you can do thumbs up in the chat. But okay, so yeah, so I press this button here on the microcontroller, and then I'm going to show you that it's working actually. So believe it. Believe that it works. All right, so, and I think I just show around here. I'll just keep it running in case somebody wants to reference it later. Yeah, and there you go. So here's the final circuit that I used. It's an LT Spice drawing, but it's not a workable model. So there's a 9-volt rechargeable battery. There's that switch, the audio amplifier board, which has a potentiometer, which I didn't really describe. You just put, eventually you can't amplify the voltage any more than the voltage input, because it's not a voltage amplifier, it's a signal amplifier. Then I used this board, which connects to the Arduino. So I have a link to the tutorial for the Arduino frequency generator connection. And here's the interesting bit here I'd like to show. If it just let me zoom in for me. Here's a current peak detect circuit. What this is this. So this is the transformer. I think I'm skipping a lot, and let me know if you want me to slow down. Because I think nobody besides me has seen this. So here's a transformer on the output, and the output for the audio amplifier is also grounded, which is nice. Why do we like grounded things as R&D engineers? Because we can put our voltage probes wherever we want. We don't have to use floating voltage probes to measure. That's why we like grounded situations. But I also very much like differential probes because they don't have as much noise and they have great bandwidth. Far more than you'd need. So we have this crystal. All right. So right now, yeah, transformer is used for impedance matching, but basically impedance matching means you have to increase the voltage to drive a higher impedance load. That's what yeah. So there's a question in the chat about why we're using the transformer. Well, because the voltage is not sufficient, but that also means the optimal impedance load of the amplifier is not sufficient. So impedance matching is like a synonym almost of voltage, as long as you have enough current to drive the whole thing. So there's a question like, why do we need to use this signal generator board here? Why don't we just use the Arduino itself? The reason we can't use the Arduino itself is because it doesn't have discrete frequency steps that are very small. It'll be just fine at low frequencies like 1,000 hertz or 2,000 hertz, but once you get into 40 kilohertz, I think the step size for the tone function in Arduino is about 300 hertz, and once you get to higher frequencies, you'll be able to you have to use assembly code and things to make it go on and off, and it's still not really that efficient. And someone also mentioned here in the comments, well, couldn't we use an RLC resonance circuit to drive it? So you still need to provide the frequency somewhere, even if it resonates. Like I guess you could do an oscillator feedback circuit, but that's not really so common now. Yeah, an RLC resonant frequency circuit, kind of attaching that to your crystal, that could be used to help amplify the voltage, but you still need to provide your frequency, I believe. So So let's see, there's some other ones. So yeah, so actually some microcontrollers, um, uh, yeah, so somebody mentioned that at 60 kilohertz, they're actually able to generate 1 hertz frequency steps using certain microcontrollers. Uh, and the Arduino is not like the high performer, even of the Arduino class. And there's other microcontrollers that maybe use the same programming, but they don't have but they're just not like as common as the you can't find the info as easily, but it's still be doable. There is a PIC microcontroller from Microchip that has what's called a NCO, a numerically controlled oscillator. I believe it's very similar to the chip that we have here in terms of how it functions, like in terms of the theory of the function, and the microcontroller itself provides very discrete frequencies just off the bat. um, so yeah. So yeah, I'll just keep continuing and I'll talk about this current measurement circuit. So here I have this 10 ohm resistor on the ground side of the crystal. So I just assume this is the high side, this is the low side. It's isolated, so you kind of just stick ground wherever you want to, or wherever I want to actually. So I stuck it here. And I had this 10 ohm resistor. You know, the voltage across the resistor is the current, so I can measure current from here. Like, yeah, using an oscilloscope probe, you can measure current. But how do you do that using a Arduino with low frequency capabilities only? So for that, we create a peak detect circuit. So this is what this circuit does. I think this is supposed to be reversed. I could check, and I'm gonna look at that. Yeah, I mean, this might need to be reversed. But basically, current is allowed to flow in one direction and not the other. So this capacitor is allowed to charge and not discharge. So when voltage goes higher than 0.7 volts, which is the drop voltage, so diodes have a drop voltage. So when it goes higher than that, then the voltage on the capacitor will get charged. And then when it oscillates, when it comes back again, so it gets charged to, let's say the first sine wave was 5 volts. So let's say about 4 volts got charged after a couple of cycles on the capacitor. Then we have a current that comes higher, like a current of 6 volts comes, like equivalent. And so then the capacitor gets charged higher. So it keeps that value because it can't drain. The charge is not draining back. You're not allowed to drop the voltage because the current can only flow one way. So I believe this diode should be flipped. I could probably check my diagram, whatever. So this diode should be flipped. And this is the white mark on the diode should be facing the capacitor. I use the capacitance value of 3.3 microfarads. And the significance of that is how fast it can charge up. I have a resistor here because I don't want the peak value to be held forever. I do want to reset that. So it's constantly draining very slowly. So if I turn off the circuit, normally without this resistor, the peak value would just stick and it wouldn't change. But I want it to be reacting to how the circuit's behaving. So it's kind of like an averaging function that's used when you use a resistor and a capacitor that you can actually monitor the live peak voltage according to how the circuit interprets it. Are there any questions about that? You can look up this circuit online. This is a kind of very simple topology. Current, or peak detect circuit using a capacitor and a diode. You Google that, you'll get a lot of results for that. And I use this specifically now because I'm doing a peak detect over a resistor, and which is also grounded, by the way. All these are grounded, the same reference point. Because I'm doing over a resistor, now it's current all of a sudden. So that is good. Is there any risk here of sending too much voltage back to AO? I don't think so, because you have to I guess I mean the diode's not gonna help. But I think the 10 ohm resistor would probably stop that from happening, because if there was, let's say 100, like let's say there's 20 volts on here, that's like 2 amps going through this. Like, it's not, I don't think that's going to happen. So there's always a risk, and we move forward anyway, I guess. If it doesn't break, then I get to complete the webinar. If it does, then I have to apologize at this point for something that didn't work. So there's no apologies happening today, except for the ones I've already done. And yeah, it worked. It didn't fry, and I did a oscilloscope measurement first to make sure the voltage was good. It wasn't like out of range, or, and it's only going to be positive, right? Because the way the diode is switched, this should be reversed. I'm just going to do it right now instead of having to say it 100 more times. Yeah. So it'll allow current to come up, charge that capacitor, but it won't allow it to drop. But it'll be dropped over this resistor, will bleed that charge off in order to reset kind of that average. So it'll be a rolling average basically. And there's a time constant here. I think the time constant is like 3 milliseconds or 0.3 milliseconds or something. 10K times 3.3 micro is going to give you a time in seconds, and that's going to be your reset time. So if you make this like 2000 microfarads, like you're not going to get any useful like rolling average. So you can do those calculations, and the best way to know if it works is to try it. I also like to turn off the device and see how fast it drops. If it drops immediately, that's perfect. So if it doesn't drop at all, based on the resistor and capacitor value, then I'm concerned. Let's take a look at the code. So I'll be sending this out as a PDF. That's why I have these little tiny code right here that you can copy later. Yeah, so I have a little tiny code that you can copy, but basically what I did was I took the code, the standard code that was provided, and I changed some of these parameters. Now, I'm not going to explain these parameters in detail because they are done here, probably with more detail than I would want to do here. So I have a standard library, and after putting that standard library in, I define the analog. I defined the read function for the analog output, or it should have been, yeah, input. Then we have the loop, we read the value, and then based on the value, I tell the Arduino if I want to increase frequency or decrease frequency. Because I'm starting above the resonance, if I decrease frequency, the current goes up. And if I increase frequency, the current goes down in general. So that's the logic I'm using. If that breaks down at any point, then the system doesn't work, and you'd have to put more logic in, but it's worked so far. So in this case, with this code, this kind of reprograms the second the clock frequency that's driving everything. If this parameter goes up, then the frequency goes down. That's how it works. So if the current, which I targeted as 60, 60, and basically the Arduino with 5 volts is 124. Oh, sorry, 1024 is 5 volts. So this is a pretty small voltage level it's reading, and and I mentioned also it's dropped over the resistor. Dropped over the diode. That's another reason I used the output side for the current measurement, because a diode on the input side, a diode on the primary side would really drop a lot of. First of all, it would drop a lot of voltage, like 0.7 volts. That might be the whole voltage you're trying to measure. And also, if I put a resistor there, that resistor would dissipate power, and that's not good. It's better to do this on the high impedance side, the secondary side. The simple logic: hey, if the current is too small, decrease frequency. If the current's too big, increase frequency by reducing this I value. And I originally had a delay time here, but I found it worked fine with 0 delay time. And here's how I turn it off. Now, this is a kind of very not intelligent, but we do what we need to. So I changed the frequency to 60 kilohertz when I wanted to turn off the device after 3 seconds, because I didn't have like a power input, a control over the power input to the clock board. So I could have maybe had a relay or some other transistor or something. I didn't. So I just changed frequency. So therefore it turns off the misting after 3 seconds. Here's my standard code again that you can just copy and directly upload to an Arduino, and it'll do the exact same stuff that I mentioned. And I set up my Arduino exactly in the same way as the as this code here, except for analog 0 that I actually use separate. Everything else is wired the same. All grounds are 1. This is my message to you today. My spiritual message is all grounds are 1. And that's the same case for my circuit here, but that's not very good for medical devices, right? We don't do that. All grounds are not one in medical devices. We have different reference voltage, and we have floating things. Keep people safe. So okay. This is the operating condition. This is gonna be a video. So let me move my head. Sorry. This is a video here. Oh, I'm on pen mode. So this is being driven. This is in the dormant mode. This is 64 kilohertz. Like I mentioned, it's dormant. It's not doing anything. It's waiting for me to press the button to reset the Arduino to run back through the code for 3 seconds until it exits and does this dormant thing again. So as you're going to notice, it just immediately finds the resonant frequency, the one that I want at the right current. Oh, there you go. It just did that really fast. So it was actually frequency tracking. You just couldn't tell. So these are what the waveforms look like. So this is the square wave input and I was planning to do it. Sorry, this is going long, guys, but I'll get through it. This will be uploaded, so you can sign off if you need to. So this is the frequency gen. The red curve is the V out. So V out from the amplifier, and this is the primary side. So this green is the V secondary, and the yellow is the current. Now the current looks pretty ugly. It doesn't look, but this is at 64 kilohertz right now, so it's a tad bit better, I would say. Beauty's in the eyes of the beholder, right? But it's a tad bit better at resonance. Yeah, so I'll be sending a link, and it'll be on YouTube. I don't tell people that before, so they can come in person, but I think it's also just more engaging to have people, and it makes it more enjoyable for me too. So this is the voltage. This is the current, right? The second one is a current, or basically voltage over resistor. So you divide that by 10, and you get the actual current. So let me just skip ahead here. So this is during actual operation. This is current waveform. This is voltage output. This is voltage output. That's secondary. The red is input. The red is primary, and then the square. It kind of goes. It's pretty logical in the order it goes into. So we have 3 volts, or I did peak to peak just to make it easy on myself. So 3.5 volts primary on the primary side, 46 volts on the secondary. So I think that's 15. Yeah, it's a multiple of 15 about. And the current is about peak to peak. It's 230 milliamps peak to peak. So that is that. I don't think I have slide numbers on here. Let me just, but yeah, I'll go. So all right. Hopefully there are no questions there. Yeah, there's a lot of harmonics here. If you drove this with a sine wave, there would be no harmonics, so that could be done, and using the chip that someone mentioned, or you can use other circuits to convert sine wave or square waves into sine. However that fits your need, but the device works, and the current amplitude that is measured by the Arduino works. I'm going to describe that in a second too. So this is also kind of a square wave like output. And you can kind of see the input. The primary side is very similar to a sine wave in a way, but remember, your transducer reacts differently at different frequencies. So naturally, at high frequencies, there's lower impedance. So the current draw is going to be higher. Even if you have 1/10 of the voltage, you may still have a decent amount of current. And this resonator here, this transducer is not all that good at resonating in terms of the quality factor. It's not good or bad, but it's just not what perhaps many of us are used to in what transducers are. So this is the current over time plotted from the Arduino. So if you see at the end of every cycle, I report the current and that the Arduino is reading, and on the serial monitor, that's the code. So it immediately gets to 60. If you see here, it's gonna freeze again, I think. So yeah, it froze. Hopefully I don't have to restart the program. It's happened before. Yeah, I think it froze. All right. So yeah, it's just about done. So the same thing would happen with frequency. You see, I'll just keep talking over this because Zoom isn't frozen. But you see here, it's gonna get to 60. Uh, yeah, I don't know. I doesn't like these screen recordings that I did. I've just having a lot of trouble with Windows in general, and yeah, I guess that's life for now. But basically the current jumped up to 60 because and here we have frequency, but I'm actually determining this I value. I'm reporting this I value, which is basically the iteration, the frequency step size that I set, which is about 100 hertz. I could have made it finer, but I didn't have to for this application. So basically also ramps up from 0 hertz. I think I can just close it and restart, I guess, and don't report anything to them. They don't do anything about it. But it also, I, I hope it works this time. If you guys see my screen, I believe. So the frequency, you'll see it. Yeah, you'll see that it jumps up quickly from 0 and it gets to this 183, which is 183 iterations down in terms of, and you can see it going around this point. So it's trying to track frequency. If the current is too high, then it backs away from resonance by increasing frequency. If it's too low, and kind of the direction of how I iterates is opposite to the frequency it goes to. And if you see this response, it kind of tracks around 60, which is what exactly we needed to do. It's probably not optimized, but it got the job done. And a circuit very much like this could be implemented in a commercial product. I don't doubt that could be done there. So right now I'll just ask for questions. I'll continue to record in case it'll be useful. Yeah, thanks for staying on so long. But I think I hope I did the topic justice as far as I was able to. So I'm going to continue to record right now, and if anyone has questions, I'd be happy to take those. And if you also have questions that you don't want recorded, I can also do that. Um, so are there any good resources for learning DIY transformer winding? So I'm not aware of that. Yeah, I wouldn't have anything to specifically report. But for lower frequencies, it's not all that hard. It's easy to wind. It's kind of a unique component that's easy to wind and try and see how your amplifier deals with it, whichever one you're using. So yeah, thanks for the appreciation. I also, for the people who are still on, would you like me to continue on this circuit next time and like mention improvements in terms of current measurement, in terms of what happens when you do a sinusoidal, like yeah. So I think it'd be kind of interesting to do. Just to continue to see and analyze, hey, what about the transformer matching with this amplifier? What about changing this capacitor on the output? What's the highest frequency it can drive? Can we weld with it? Probably not. You can put two together and you can drive with more voltage because you can kind of make the output isolated. So so there's like, yeah, a lot of different kind of good analysis that's possible with this. But yeah, I even think that this product as it is could be like you could put it into an atomizer circuit. It'd be kind of expensive, but somebody could use it. um, yeah, so improving impedance matching using inductors. Yeah, that's also good. Yeah, the another problem thing that you can do, because this load is so capacitive, um, like you can see the maximum phase is -25. It won't be this good when you drive with high voltage. With the high voltage, the maximum phase will probably be -60. So it'll be very capacitive. You can intentionally exploit that by using an LC resonance. You could put an inductor, and now you have a resonator, and you don't have to even use a transformer. You may need to protect from like back voltage once you turn it off, but otherwise you'd be in good shape just using you could amplify voltage that way. But this is like the most straightforward, least amount of. This is like basically a circuit that took the least amount of tinkering around. Yeah, I'm kind of excited that I was able to bring it to you. So I'm going to stop my video or recording.